Okay. Yeah, the interesting thing about calculus is not really the calculus. Well, I mean, it is. The calculus itself is pretty interesting, but it's the kinds of things you can do with it lots of times that are super cool. So let's look at something like this. We've got these two functions, y equals x squared and y equals negative x squared plus 6x minus 5. So let's just graph this so we can get kind of a visual sense of what is going on here. So let's graph f of x equals, or y equals, won't be so fancy, y equals x squared and y equals negative x squared plus 6x minus 5. Okay, so based on this picture, can you kind of see where there's going to be two tangent lines? Okay, you could get, it looks like maybe there's going to be one, well, let's see, we could draw these if I zoom way in. Right, it looks like maybe maybe we're going to get one, oh, kind of like right there if I extend that guy. Does that make sense? Oh, let me do that. So there's kind of one, right? And maybe here's another. Oh, that moved. That moved the wrong way. So what happened when I?
Oh, it's when you pull out the
shapes pop out.
Oh, I got you. Okay, I got you. So it'll go back.
Yeah.
Okay. I got you. So then we're gonna have one kind of like maybe. Let me just copy this one. How about just tweak it a little bit. So this one maybe goes like. You get the idea. It's going to go up from up here, maybe down there somewhere. Right, you get the idea. So we're going to get two different lines that could be tangent to both curves. Right? We can visualize it, but we don't really even need to visualize it. I mean, we can see that it's there, but the calculus, you know, the math gods they'll take care of it for us. We don't even have to do a graph. How are we going to set this up, do you think? How are we going to go about trying to find these two tangent lines? What are the ingredients of a tangent line? A slope and a point, right? And by a point, we mean, you know, a point of tangency. So why don't we, maybe I will just put up one quick representative example here, just so we can kind of orient ourselves with how we're going to set up these math equations. So we've got the equation y equals x squared, which is like that. And then this guy's going to be going down. If we factor that, what are we going to get? Negative 6. So 5 and 1 would be the intercepts. So something like this, where it's going to go kind of like, that's pretty bad, but you get the idea. Okay, so here's going to be, let's say here's one of our tangent lines. It's going to go between those 2 points of tangency. And the thing about math is we don't have to, all we have to do is set up the math so we can treat a general case. So we can write equations that are going to work for some representative tangent line, and the math gods will give us all the possible solutions of that general setup. Okay? So we've got a point of tangency here and a point of tangency there. Let's call the blue curve, as it's further to the left, let's call that one curve 1, and the yellow one we'll call curve 2. So how could we label those points of tangency as ordered pairs, do you think? Suggestions, and this is all new to you guys. We're just gonna kind of start, this is really good to go through a big problem like this and just talk about how we think about it in that. Suggestions. I don't want to use probably just plain old x and y because those are variables, right? These are functions, like this function right here, y equals x squared. X and y are variables because they represent the locus of all those infinite points that match that pattern, right? So I don't want to just use plain x and y, but why don't I do something like this? Over here we'll say that this point of tangency right there has coordinates x1, y1. So I'll put some subscripts on there. And those subscripts are telling us that those are specific values of x and y that we attach to that point right there, the point of tangency on the first parabola, okay? So then by extension, what are we going to have probably down here? Yeah, so that we could call these points x2, y2, okay? So tangent lines, we need a slope, right? We need a slope. So what are some ways that we could come up with naming a slope? Say it again. Okay, right. Well, I see what you're saying. Yeah, so we know how. I got you. So we could do derivatives, right? Good. And I'll put that. I got you. So we could use our general rule. We could say the derivative with respect to x of some constant times x to the n equals c times n times x to the n minus 1. We'll make use of that, for sure. How about before we even jump into the calculus, I've got these 2 points of tangency. The tangent line that we're talking about has to connect both of those, so suggestion. Yeah, so we're just going to find a plain old slope between those points, right? So one thing we could say is that the slope of this tangent line is just going to equal, using just the points of tangency, the slope of the tangent just has to be y2 minus y1 over x2 minus x1. Right? Everybody agree? That's a true statement. What else, though? We can also attach slope to the calculus concept of a derivative, right? So what's another way that we could say the slope of the blue curve at that point, which is the same thing as the slope of the tangent line? So we'll make this one blue, right? Because this is my blue function right here, isn't it? So what's the suggestion? Take a derivative, right? Take a derivative. If y equals x squared, right, then we'll just call it y prime, right? The derivative of the blue tangent line is what? 2x. Okay, right? So we could use that. We could say at the x value, x sub 1, right? Another way of writing that would be to say, we could write it as y prime. We've got all these different notations, and they all mean the same thing. But sometimes it's more useful to maybe write it in one way or another. Another way of saying that would be if we're going to call this, let's say we call this one f of x, right? So we could also say f prime of x equals 2x, right? So really, if we want to know what the slope is at that point, we're just plugging in x1. We're evaluating the derivative function at x sub 1, right? Okay, so then we'd end up with something like f prime of x sub 1 equals just 2 times x sub 1, right? That's the derivative, isn't it? So would you agree that everything we're going to put in pink is going to be equal? So that has to equal that, doesn't it? They mean the same thing, right? They're both slopes of the tangent line. Because isn't that what the derivative means? Right? F prime of x is telling us the slope of any tangent to the blue curve at whatever x value I input. So if I input what we know to be the point of tangency, then it's the tangent of the green line, right? Okay? How about if we use the yellow point of tangency? Okay, so here's our yellow function, right? So what's the yellow y prime? Plus, okay? So we could also write that as, if we call this one, how about g of x? We could write that as g prime of x equals negative 2x plus 6. We don't have to do it that way. But my point is then just that we could say g prime of x2, x sub 2, equals negative 2 x sub 2 plus 6. And so that also gets a pink box. Because all three of these things must be equal, right?
Must you get the negative terms?
How'd you get it? Richard, how'd you get it? Come here.
Just do
That rule, right? So we're going to take the exponent down front times negative 1 and then subtract 1 from it, right? And then next term, derivative of x to the 1 is just 1, right? And then the constant, derivative of constant goes away, goes to 0, okay? So now what? How can we come up with, how many unknowns do we have there? Because we want to start thinking about this strategically. If you look at those three equations, how many unknowns do we have? I count 4. x1, y1, x2, y2, right? How many equations do we have? Well, I mean, we could set those equal to each other, right? We could set those equal to, we're still missing something though. How about those darn y's? How can we deal with the y's? Is there a way that we could eliminate a couple of variables there? Because that's always our goal. When we're solving for more than one variable at a time using more than one equation, we just call that a system, right? We want to minimize the number of unknowns in the system. Is there a way that we could somehow deal with the y2 and y1 and get rid of the y so we can just have x's?
Did you put in the lines on
Yeah, look, we know, here's the blue function, right? That's the function that relates y1 to x1, right? Wouldn't you agree that y1 is just x1 squared then? Right? Because that's a point. x1, y1 is a point on that function, right? So it's got to be a solution, right? Let me not just add those subscripts. We'll make the point here that we have another equation that's going to work. We can add to our system. We could say y1 equals x1 squared. So there's a substitution equation. Okay. How about on the other side? Well, y2 must equal negative x sub 2 squared plus 6x sub 2 minus 5, right? There's another substitution equation we have. So if I make those substitutions, we've now only got, it's kind of a mess, but we've now only got 2 unknowns. And we ought to be able to solve a system of 2 equations and 2 unknowns. I mean, it's not always the easiest thing to do, but we can, right? So we could make this substitution and this substitution. Well, it's kind of messy right there. Okay, you did, yeah. And then we end up with, right, we're going to end up with some equations involving only x1s and x2s. Okay? What do you think? I think I'm going to, I'll make this like a challenge question. we'll come back. And I'm gonna let you guys take it from here if you want to. I'll make this worth your while to do though. Okay, I mean, this would be kind of a cool one to do. I don't know, do you wanna just continue going through it, or do you wanna work on it? How many people wanna give this one a crack on their own? Anybody? Couple people? Okay. I know what I'll do. Let's finish this one, and then I'll give you another one for a challenge just like it. So we go all the way through one. Hey, I'm teaching. Yeah, what's up? Yeah, they're waiting for me to hang up the phone. Yeah. Bye. Mr. Hagewood. Let's finish this one up, and then I'll give you one for like a. I'll figure out some. I'll attach some kind of a fabulous gift and prize to it. How's that? So how can we set up these equations then? Let's take this guy, and what's it going to become? Okay. Every place we used to have a y2, we can now make this substitution, right? So we're going to end up with. It's going to get kind of ugly, but we're going to get a. This becomes negative x2 squared plus 6 times x sub 2 minus 5 minus y1, which is just x sub 1 squared over x sub 2 minus x sub 1 is another name for our slope, right? So now we've got 3 different names for our slope, and so we ought to be able to solve this system. We can connect any of these boxes with an equation, right? So what do you think? What might be a good way to connect those boxes? Okay, so say that again. Okay. Okay, so the negative x2 squared, and then right here. So you were trying to see if we could coax out like an x sub 2. Unfortunately, those are both negative, because you would maybe think about factoring them or something like that.
What does the 2 have to do with the value? Nothing? Is it just to denote?
The sub 2, you mean?
Yeah.
Yeah, well, they're just distinguishing 2 different points.
Okay, so they mean nothing in this equation.
Well, no, it does, because when we're all done, it's a good point. What are the math gods going to tell us? How are we going to know when we're done? What are they going to give us? They're going to give us values back of x1, y1, x2, y2. What are those?
Points.
Points of tangency, and that's really what we're looking for. If we knew what the points of tangency were, we could find the equation of the tangent line, right? Okay, now let's look at this strategically. What is so incredibly ugly about this equation right here?
Subscripts.
The subscripts make it tough because they don't match up. Is there a way that we could write x sub 1 in terms of x sub 2, for example? How?
Taking the 2x subscript 1 equals.
Yeah, see what I'm saying? We could, if we took these 2, so here's the idea, we're going to take, I need new color here. I'm running out of colors. So if we took this one and that one and use that equation, what are we getting back? So 2x sub 1 equals negative 2x sub 2 plus 6. Divide both sides by 2, and what do we get? X sub 1 equals 3 minus x sub 2. Right? Everybody agree? Okay, that's good. If I make that substitution, then up here, look what happens. Every place I had an x sub 1, I'm going to replace it with x sub 2's. And I get a slope involving only x sub 2's, right? Everybody agree? And so then if I took that result and I set it equal to another expression of the derivative that involves only x sub 2's, like that one, I ought to be able to solve for x sub 2. You see, I mean, you see what kind of the strategy is here? If you look at this, this is a really hard problem. I mean, this is way above and beyond anything that I'm going to give you guys like on a test. I mean, but I just want you to see kind of how, what's the thinking process here. When we're trying to solve a complicated system like this, you correctly identified that the big red flag is, well, we've got all these 2's and 1's in this. I mean, what's that mean? How are we going to do anything with that that's going to simplify it? It's not going to, right? It's really tough. We've got to make a substitution because we've got apples and oranges here, right? So if we can make a connection somewhere, an easy connection between x sub 1 and x sub 2, then I could come up with a substitution equation that I could use to eliminate a variable. And think what substitution equations do. You probably never really thought about it. Subconsciously you did. But let's percolate this up to the surface and make it a conscious strategy. When you want to eliminate a variable, you substitute. You come up with a substitution equation, right? That's how we do it. Right? So here we've got a way that we could say every place we've got an x1, we can trade it for some expression involving x2's. So we're going to end up with some function down here, some expression that only involves x sub 2's, right? So does this one. So then I can set those equal to each other, right? And solve for x sub 2. Because how many equations do I need to solve for a single variable? Or for one unknown? One. That's it, right? One. Okay? So what happens if we make that jump then? If we make this substitution, so we're going to let these x sub 1's become 3 minus x sub 2. So then let's carve out a new space down here. And we get negative x sub 2 squared plus 6x sub 2 minus 5 minus the quantity 3 minus x sub 2 squared all over x sub 2 minus the quantity 3 minus x sub 2, right? Yep.
Couldn't you go even further with the 2x sub 1 equals negative 2x sub 2 plus 6 and just solve for x sub 2 minus x sub 1 to deal with that bottom part?
Okay, we could, but if I solved for x sub 2 minus x sub 1, I can substitute in the bottom conveniently, but not the top.
Yeah.
Right? See what I'm saying?
Yeah.
And so as a general rule, when we're, it's a good point, but as a general rule, when you start to get into really higher level math, when it's really convenient to do, you can take big bulk substitutions like that, which we'll oftentimes do. But if there's a lot of different individual substitutions in a problem, you have to just trust me on this one. Having done problems with hundreds of pages of algebra in college several times, it's just easier to avoid mistakes if you bring everything back down to one substitution so you can debug it later if it doesn't work. So you can say, okay, this is the substitution I made. You can trace, because realistically speaking, I'm just telling you, I spent probably more time doing in my grad school and college classes in math problems, finding mistakes than doing the algebra. You spend most of the time trying to figure out where you screwed up, and there's lots of math to follow, and so it sort of forces you into a pattern where you're gonna try to go through your work in a way where it's easy to trace the individual steps. Now we're like looking, so honestly, I mean, this is a hardest class. It's a great class. First year calculus, you only get to do it once. It's a great class. It's fun, but if you're looking at a long-term trajectory that involves math, whether that's directly or indirectly, you're going to look back in a couple of years and say, oh my God, that stuff is so simple. I mean, it's just first year calculus, it's not that big a deal. And so it's hard to kind of think in terms of some of this higher level, like long-term thinking. But I do want to get you, that's kind of the purpose of doing problems like this a little bit to me, is it gives you confidence, for one thing, that you can do this stuff. And that's big. I mean, sometimes in math, I got to tell you, this is a little side note here. Sometimes you're just faced with problems where you just go, oh my God, how could that ever work out? But I promise you, if you just, inch by inch is a cinch, yard by yard, it's way too hard. You just take it kind of step by step, and you just do things, you're careful, and you do things mostly correctly, you will, you will find your mistakes as you go, and it all just magically works out. The math gods are they're very benevolent deities. Yes, they're there to help us out. And so if you just kind of have faith and trudge through things, it's amazing how often stuff just kind of like, oh my God, that's it. I got the answer. It works out. Been there 1,000 times. Anyway, back to the nitty gritty. So we've got this. So this is a re-expression of what we had here where we make our substitution. So now we've only got x2's involved, right? So now we could set this equal to this, right? These are two, where's my pink box there? Right there, this. Okay. Here's two pink boxes that both involve x sub 2's, right? This is kind of a weird way to show all this work. I can't really do this like where I just write down a page because you wouldn't be able to see everything, but in a way I kind of like this, where it's just sort of a graphic organizer, right? We know that all these things represent the same slope, so they're all equal, but here's two convenient pink boxes that have x sub 2's only. So I can link those with an equation and solve for x sub 2, right? So what do we get? If we take this guy and set them equal, we need a new page. This is getting way too messy.
Yeah.
So, okay, set those equal and solve. So negative x squared, start with this one, plus 6x sub 2 minus 5 minus, let's distribute the negative, minus 3 plus x, oh no, hang on, I gotta square that whole thing out, don't I? Whoops. So help me out, what is that? If I square this whole thing out and
X
distribute,
squared,
what am I gonna get?
X squared minus 6x plus 9
Okay, so x squared,
minus,
so it's gonna be minus, when we distribute the negative, we'll make it a plus.
Yeah.
And then
minus
minus 9, right? Did I get that right?
Yeah.
Okay, good. Okay, all divided by 2x sub 2 minus 3. If I distribute the negative and add like terms, everybody agree? Equals negative 2x sub 2 plus 6. Number 1, maybe you want to write it that way. So what can I do to solve this now? I've got a ratio equation. What's oftentimes a good thing to do then? Say it again. Cross multiply, right? Were you thinking about reducing or something? Oh yeah, okay, for sure. Simplify that while we're at it. But then we'll cross multiply too.
Simplifying that comes out to negative 2x squared plus 12x minus 14.
Negative 2x squared. When we say x now, we mean x sub 2.
Yeah.
Okay. Negative 2x squared plus
plus 12x
12x
minus 14.
minus 14 equals that times that. So what's that going to give us? If I'm going to multiply this guy times this guy, right? So let's go ahead and just let's just expand that out. So I'm going to get what? Negative 4x sub 2 squared plus 6x plus 12x. Right, if I combine the cross terms, negative 2 times negative 3 is positive 6, x sub 2, and then when I distribute this guy, I get plus another, oh, it should be 12, shouldn't it?
Yeah.
12, not 18. Yeah, 12x sub 2 minus 18, right? Is that right? Double check me on that.
It was 18.
So let's see, here's one distribution. Did I get that right? So negative 4x squared plus 6x plus, oh, it is plus 12x. What am I saying? So that is 18, right? So that's an 18. And then minus 18. Everybody agree? Okay, so how many unknowns there? Well, x sub 2's, right? So we're just going to push everything over to the left and make a quadratic equation in standard form, right? So then we end up with what? So we get, if I add 4x squared, I get 2x squared minus 6x plus 4 equals 0. Okay, I could divide both sides by 2, agreed? Okay, so that's going to give me x squared minus 3x plus 2. And what are numbers that multiply to positive 2 and add to negative 3? We can factor this. Yeah, so it becomes x sub 2 minus 1, x sub 2 minus 2, right? So what are my solutions then? So either x sub 2 equals 1 or x sub 2 equals 2. Does that make sense in the context of our original picture? It does, doesn't it? It does because there were 2 tangent lines, right? So that means there must be 2 possible points of tangency on this curve, right? The math gods just gave us both. From here, it's easy sailing. Now, we did all the hard work, right? From here, I would just say, okay, so what if we take the one where x sub 2 equals 1? Well, how do I work backwards and find what all the other stuff is? If x sub 2 equals 1, you can go back to this page. How am I going to figure out what y sub 2 is? Yeah, where's that?
It's,
Oh, right here, right? Everybody see that? So I could plug in 1 and get y sub 2, okay? If I start off with x sub 2, how could I find x sub 1? Right, where's that equation? Right there, right? Our substitution equation that linked x2 and x1, right? That's going to allow us to solve for x sub 1. If I know what x sub 1 is, I can go up here and find out what y sub 1 is, right? And if I know all that stuff, I could find the slope really easily. Like now, for example, I could use either one of my derivatives. Like how about this one right here? Y prime equals g prime of, well, if that's an x sub 2, right? Because this is coming from the sub 2 equation, I could plug in x sub 2 there and find out what the slope is there. Or I could go back over here and plug in x sub 1 into this equation and find the same slope. Or I could don't even use calculus. I could go up here and just use this, right, to find the slope of the tangent line. Take your pick. It's an embarrassment of riches, right? You got all these different options available. And so we'll just do that for each of the 2 x sub 2 values that the math gods gave us, and we'd find those tangent lines, right? How much time we got? Oh, so we can do it. Okay, so let's. It's just fun. There's a real when you finish it, it's just a feeling of satisfaction. You know, this is mathematical satisfaction. That's good. So if we take x equals 1, then let's figure out what all the stuff that goes with it. So P2 equals 1 something. Okay, well, what's the something? We skip back to the last page real quick. X sub 2 is 1, y sub 2 is what? Go right here. So what's that going to give me? Negative 1 plus 6 is 5, minus 5 is 0. Everybody agree? So we get the point P2 is 1, 0. That's 1 point of tangency. Okay, what's the P1 that goes with that P2? So if x sub 2 is 1, and this is going to be our orange one, right? We'll pick a different color for the other possibility. If x sub 2 is 1, then x sub 1 is 2. Everybody agree? 3 minus 1. Okay, so x sub 1 is 2. Add that to our list. What's y
It's gonna
sub?
be 4.
Say it again.
Isn't it gonna be 4?
Oh, I don't know. You tell me.
Because you plug it into the y1 equals x sub 1 squared.
Oh, yeah, right there. Good. Yep, y1 equals x sub 1 squared. So if x sub 1 is 2, y1 is 4. Okay? So these are the two, here's one possibility for the points of tangency. On the first curve, we get to point 1, 0. On the second, actually, that was the second curve, wasn't it?
Yeah.
That's the, this is, I should write this down. So that's x sub 2, y sub 2, x sub 1, y sub 1. Those are values that work. Let's get a slope to go with them. So how about if the easiest slope would be to plug in x sub 1, which is 2. There's a really easy formula for slope right there, right? F prime of x sub 2 is just 2 times x sub 2. So what was it, 2 again? So the slope is 4? Is that right?
Yeah.
X sub 1, I gotta double check. X sub 1 is 2.
Yeah.
So here's our problem, this is curve 1. So y prime is just 2 times x sub 1, which is 4. Okay? So there's one case solved. Okay, what about the other case? So the other case, we've got, what's a new color here I haven't used? We'll use that one. Was that lavender? I don't know. So what if we pick x sub 2 equals 2? Of course, day's not complete. So what if we take x sub 2 is 2, then we got to find y sub 2, so we'll go through the same chain. Go back here, let's see, x sub 2, where was that again? Right here, right? Here's the one that links y sub 2 to x sub 2. So negative 2 squared is 4, so negative 4 plus 12 is 8, minus 5 is 3. Everybody agree? Did I do that right? Okay, so y sub 2 is 3. What about x1, y1 then? So we're starting with x2 is 2, so x1 is 1. 3 minus 2, okay? And then we got to find y sub 1. So that's easy. That's just x sub 1 squared, right? So right there, right? So 1 squared is 1. So 1, 1. And now the slope of the tangent line is going to equal, let's use the easy one. So x1 is 1, and the derivative is just 2 times x sub 1, so it's 2. Okay? Okay, so now we could easily turn these into tangent lines.
Almost.
Almost. Yeah. I'm kind of amazed we finished that problem. It's a big problem.
Is that ever gonna be on site?
Well, I'll give you a chance to do one of those. Okay, so the orange tangent line then, now it's just algebra 1, right? So we know, actually, look, we even know, well, no, we don't. It's not the right intercept. But we could use either one of these points. We know the slope is 4. So the orange tangent line is going to be y equals 4x plus b. Let's borrow that solution because it's easy, right? So we could plug in 1 for x, 0 for y, and that gives us 0 equals 4 plus b. So b equals negative 4, right? And so then that tells us that we get y equals 4x minus 4 is the orange tangent line, right? How about the lavender, pale lavender line? So we get y equals 2x plus b, let's borrow that solution, that's easy. So 1 equals 2 plus b, b equals -1. So we end up with y equals 2x minus 1. So there's a tangent line. There's a tangent line. Let's go back and add those to Desmos and see if they work. See if we didn't screw up in there somewhere. Seems unlikely, doesn't it? So much math.
Wow.
Somebody here told me yesterday that they wanted their brain to hurt today, so I took it at face value.
The words sound so well though.
Yeah, I think it was.
Oh yeah,
Yeah.
the words sound so well.
So let's try it. So then we get the line. I'm just gonna. So here's, you probably can't see this, but I'm putting this in Desmos kind of as we speak here, and I'll show you what it looks like. So y equals 4x minus 4. Boy, I hope this works. 4x minus 4. Hey, check that out. That looks pretty good, doesn't it? Woo! Look at that. That's a thing of beauty. There's one tangent line. And then here's the other one. Y equals 2x minus 1. Oh my goodness. Look at that. Oh, look at that. Wow.
Where did they intersect that?
That's pretty amazing. How about that? And so let's find
That's easy though. Like,
let's find those points of tangency. Well, there's one right there. Oh, what do you know? 1, 1. And there's another one right there. Oh, hang on. What do you know? Where's that point of tangency?
Is that intersection right there?
How come I'm not?
Your
I did?
attitude is really.
should be a 2, 3. Right there.
Oh,
How come it won't stick? I don't know, but anyway, that's a wrap right there.
Very nice. I like how after you get done with the one part, it's just all breezy because you already have
Yeah.
everything.
Yep, you did all the hard work, and then it's just picking up the pieces.
This way.
Oh,
Yep.
It's almost like the first stage of the writing one.
Yeah, yeah. So, that one right there?
That looks like nonsense.
Yeah, it does. It does. Yeah, seriously, if somebody walked in to look at that, they'd be like, my next class will be so afraid if I leave that up there.
This is easy. Easy math. Easy math.
here, today.